First of all, we're going to hear from two physics teachers who are teachers at Legae Academy. And then they're going to tell us a bit about the astronomy component of the physics syllabus. And then we will hear from a panel of 4 students from Legae Academy about how the universe has revealed its secrets. So to get the ball rolling, I'll introduce to you Mr. Otositswe Setlang and to Mr. Tangai Charamba. Both these men are teachers of physics at Legae Academy, and it is greatly to their credit and to the credit of the school that their school's astronomy club is so active and so strong. Mr. Setlang is a Botswana who received his bachelor and master's degrees in the UK and has been teaching at Legae for the past 13 years. Mr. Charamba is from Zimbabwe, where he received his bachelor and master's degrees. He has been teaching for over 30 years and has been at Legae for the past few years. They are going to tell you first, Mr. Setlang, and then Mr. Charamba, about the physics syllabus and its astronomy content. Over to you, Mr. Setlang.
So would you like your camera on?
Yes, please, so that I can see myself. Thank you, Mr. Slater. Thank you, everybody. Good evening. Like he has introduced me, I'm a teacher at Legae, offering physics at IG level. And then very, very much interested in astronomy. And I'm part of the club that runs this department or this field. What I've done is that as I was covering the syllabus, I realized that there are a lot of questions on some areas which I've noted down that maybe I might get help from you as also members of this field. We're looking at the planets to start with. It was once said that there were 9, and then now it is said that there are 8. One has gone to be a dwarf. Now, the worry about the planets, the students, is that if Pluto became a dwarf, do we foresee that other planets are also going to reach that stage of dwarfness? Were there more planets, even after Pluto, that maybe have gone dwarf? So that is the question that I get from my students. So those are the questions that I'd like you to maybe to assist with and provide answers on as I make my presentation. Now, this topic is vast. It's vast. It's beyond understanding of the students. I must admit also myself. So we talk about the distances. There are in billions of miles. We talk about the radius, the diameter. All those are in large scales. Now, to move on to the next slide, which I am failing. Charles, can you come and help me to move to the next slide? Oh, there we are. Thank you, sir. Now, another interesting fact is about the life cycle of stars, of a star. Now, the question that I encounter is, does the number of stars in the universe reduce as the stars goes through their life and their life cycle? That is a question that students fire at me, and unfortunately, I can't fully answer them because I also don't have that much information. And also the materials that make the stars from the Big Bang, is that material ever there? Are we having information of other new stars as we go on? So those are the questions that come from students that I have in this club and also in the syllabus as I offer IG. So maybe those are the areas that we might even have to invite one of members of the Botswana Astronomy of Botswana ASB to come and meet our students in the club, to come and meet our Form 5s, and maybe A-level students, as Mr. Charamba, my colleague, is going to be talking to advise us on some of these topics. Now, the other thing that arises a lot of curiosity is the black hole. The black hole is said to be that region out there in outer space that has got so much energy that it pulls everything, including light, within it. Now, the question that I meet from my students is those sucked in objects, what eventually happened to them? Do they die? Do they get to damage? That is the question that I have to face, and I have little knowledge on that. And the other question is the black hole, is it getting bigger or smaller in size with time? That is something also that that I need a light on. So if you are with me, maybe you should be noting down these questions that I meet with my students, maybe to assist on that that aspect. And then the last one that I have is generally on the universe. The question is it possible to go back in time with any machine, with any device? Is that possible? And all I can say is, I don't know. And then the other thing that I also meet is that is there life also in the other universes, or is just us on our solar system? So also that is what I face also. And then we are told that the universe is expanding. Now, this expansion, will it ever stop? Or is going to expand non-stop? And then what is going to happen? Are the distance going to increase and increase indefinitely between bodies? And then, with that in mind, just for the sake of doing well in Cambridge in the examinations, so what we usually do is that we just go through the objectives and then try to memorize, I must admit, the objectives of the syllabus so that the students can do better in the exams, even though there's little explanation because of little knowledge, but it's important that we memorize these things, the figures, light year, the age of the universe, and many other figures, radius of the universe, of the solar system, and all those, so that we can be able to do well in our examination. But I think I will write a letter to ASB to request that maybe we need a presentation on that based on our syllabus objectives, so that our knowledge can grow and grow and grow and be better placed to explain further on astronomy. With that, I come to the end of my presentation. Thank you, and thank you, and thank you.
Thank you, Mr. Setlang. Thank you very much, Mr. Setlang. I'll now ask Mr. Charamba, who's also a physics teacher at Legae Academy, to address us. It takes a little while because they have to set up the computer and connect them up again, but we're about there. Mr. Charamba.
Would you like the camera on?
Okay, that will be fine.
Okay. Turn off the speaker.
Okay. Thank you very much, Mr. Slater. I would just like to talk about the content of the astronomy syllabus at the advanced level. I teach that. It also prepares our students for the insights that go with the content that is related to the subject. We will also look at how does it relate with the natural events. The question arises is, are our students prepared to explain how astronomers know dates and times of events such as lunar eclipse, solar eclipse? What we get to know is that these events are predicted accurately, including the date, time, and regions where it will be observed. How is the calculation? And are our students ready to give counsel on the dangers of the radiation that comes from the sun, especially during the solar eclipse? Because I understand it is very dangerous to be looking at the sun in such a situation with the naked eye. So, but what we're going to look at is that the A-level syllabus looks at the standard candles. They look at luminosity and the radiant flux intensity. I'll go through the syllabus and the objectives that the students have to understand. Then we'll summarize. The students have to understand to also know the standard candles and understand how they can use those to determine distances between galaxies. They would also want to understand that this is luminosity is the term which is used so that it is the total power of radiation emitted by a star. And they also need to be able to calculate using similar shapes on radiant flux intensity. And if they have done that, they have to talk about Wien's displacement law and the Stefan-Boltzmann law. And this is the relationship between the wavelength of the radiating star and the temperature. And our students have to go through this kind of knowledge, and they have to be able to explain these and understand them. Then we come to the Hubble's constant. Generally, the Hubble's constant, in essence, it helps us estimate the age of the universe. And the students also have to know about redshift. This is coming in a bit easier on the students because they have already done the theory that allows them to understand that when the apparent shift or the apparent increase in wavelength, the apparent increase or decrease in frequency as objects move away from each other. So having understood this in the first year of advanced level, when you are applying it at advanced level, where we teach this, it becomes a lot easier for the A-level students. So explaining redshift is easier to explain to A-level students. But when they now come to the club, it becomes challenging to the Form 1s because they are now trying, because it's all this is in the abstract domain. it's not practical. It's not something that you can get into a lab and do practical experiments that you can have students do. The other theory that is also intriguing is the Big Bang theory. And it comes in with its misconceptions and its misunderstandings. The older version of the Big Bang theory was a lamp which then exploded, and internet being internet, it carries all that. And yet when when it's now being explained now, it's the universe started as small, and this, when you are talking about the background microwave radiation that can be used to trace on every part of the universe, that shows that everything should have been at the same place at some point. And then it becomes more easier to explain the Big Bang theory rather than just as an explosion. As we conclude, I would just like to say, well, at Legae Academy, we do have this content being taught in A level, but we have a club where you have all students coming in, and you will find out that our A level students are a good resource. They are very useful. They are able to explain. They can go to the level of the other students to try and explain to them these difficult concepts. They have been very instrumental. So I would think that in future, we will teach this content to the A levels earlier, so that when they will have done it at IG, when they do it at A level early, they will be able to simplify. They have been a wonderful team to simplify. The challenge that we have is that the content taught at advanced level and the content that there is on the subject is quite abstract. You just have to imagine. You just have to use the imagination. The content is also difficult because it is not easy to come up with practical experiments that can be done to help explain. But the content is exciting. So it has to be a balance. You bringing in exciting information, but which has to be understood, so that the young minds can also enjoy the subject. And then, like I have said earlier, when they're talking about the Big Bang theory, it's quite intriguing to the young minds. As opposed to what we have always known on how the universe has been to be. And then this is bringing in a different dimension. And then it is that mixture. The same can be said about the redshift. Before you learn about this, it becomes difficult to understand it on how exactly this happens. But after the advanced subsidiary level, it is easier to understand and be able to explain to others how these things work. So the A-level syllabus has its content that the students have to understand and pass. Exams will be set for them to pass on that subject. So which may not necessarily address the natural events then in the simplified mode, that we would like it to be. So there is a lot of gaps that are created in the content that we are having to teach, and what we just see in nature. And then this is where perhaps if the association can help us marry the two, to say what we are learning here and what we see just as ordinary people in the universe. But I think the introduction of this association will be very handy and very helpful. Thank you very much. And okay, I think, let me mute.
Thank you very much to Mr. Charamba and to Mr. Setlang. It's good to hear that, astronomy is quite strong in the schools, even if it's taught at A levels. And I must compliment these two men and the school that they are able to get so much interest into astronomy. And of course, if the ASB can help, that's what we're here for. We'd like to be able to do that. Okay, that means the next part is where we will have 4 students from Legae Academy. That's Makanakaishe, Muzonzini, Keto, Mokopi, Dsouza, and Raza, Hasan. They're all members of the Legae Academy Astronomy Club, with Raza as their coordinator. All of these young people have found themselves drawn to astronomy, they tell me, by the curiosity in things like the possibility of life on other planets, or perhaps black holes and what happens in there. And they're also intrigued, as Mr. Charamba suggested, by how you can understand in everyday terms what the theory is telling us about, which is often a bit obscure. Anyway, over now to Raza and his team and how the universe reveals itself. Over to you.
Good evening, everyone. I'm going to be using Mr. Setlang's laptop here for my presentation. Is it working? Is the screen popping up? Is it showing on the?
Yeah. It's fine. Yeah.
I'm going to be talking about how the universe revealed its secrets. So before the huge telescopes we have today, such as the James Webb Telescope and the Hubble Telescope, the olden astronomers used natural events in the universe to figure out the mysteries behind it. So the first topic we're on is the image of the solar system. The solar system is a huge system consisting of all the planets. So, and humans managed to map it out, but the earliest model was the geocentric model. The geocentric model was an ancient concept with origins dating back to the 6th century BCE. And you can see here in the diagram that they place the Earth in the center of the solar system, as in the center of the universe. They believe that the Earth was the center of the solar system and everything orbited around the Earth, including the sun, which today we know was not correct. And this was the most dominant view for 1500 years. And the geocentric model remained standard in Europe and the Middle East until the 16th century, when the heliocentric model proposed by Copernicus gained prominence, leading to the Copernican revolution. However, Copernicus did not create the heliocentric model. In the 3rd century BCE, Aristarchus of Samos proposed the first heliocentric model, and he placed the sun at the center of the universe. However, since the geocentric model was so dominant, his heliocentric model was discarded and overlooked. How in 1543, Nicholas Corpentius published his De Revolutionibus Orbium Celestium, his modern version of the heliocentric model, and it placed the sun at the center of the solar system. And since, due to scientific discovery, people realized that the Earth was in fact not in the center of the solar system. And by early 1600s, Galileo, a renowned astronomer, brought proof using phases of Venus that supported the Corpentius' model. However, there was still a key feature missing in the heliocentric model. As you can see in the diagram, the heliocentric model proposes that all orbits of all planets are perfectly circular, which is not true. So a Danish astronomer by the name of Tycho Brahe made thousands of extremely precise measurements of stars and planets, far more accurate than any before him. His data on Mars was especially detailed. He had the most detailed data on Mars's orbit than anyone at the time. So with an unusually eccentric orbit, which made it impossible to fit into a circular path. And this data contradicted the long-held belief that celestial bodies moved in perfect circles. However, it was not Tycho Brahe who found out that the orbits were not circular. It was actually his assistant, a German astronomer by the name of Johannes Kepler. When Kepler came along, neither the geocentric nor the Copernican, there's a little typo there, I think, models fit the precise data from Tycho Brahe's observations. So he had the data he had Tycho Brahe's data of Mars, and he would try to fit that data onto the proposed circular orbit, and it wouldn't fit because Mars is not in a circular orbit. So Kepler discovered that orbits were elliptical, or a squashed circle, they called it first, not circular, which was a major breakthrough that finally made the heliocentric model work perfectly. With Brahe's data, he formulated the 3 laws of planetary motion. So in the early 1600s, Johannes Kepler published his laws of planetary motion, describing elliptical orbits instead of perfect circles, which provided a more accurate model for the solar system. Now, next, we're going to talk about the universe, and I'm going to let my colleague Keto Mokopi take over.
Thank you, Raza, and it will be up to me now. So, long ago, about 13.8 billion years ago, the Big Bang had occurred, and as a result of this, the universe began to expand rapidly, and then but slowed down almost instantly due to gravity. But however, 5 billion years ago, it's just not here, but it's something to add on. 5 billion years ago, the universe rapidly began to expand due to dark energy, which was theorized by astronomers. So after many observations by astronomers on the spectrum of color emitted by galaxies, it was concluded that the light from galaxies further away were elongated and stretched, making the light shift, giving it a redder color. So this phenomenon was later concluded to be known as cosmological redshift. Now, okay, we'll come. Don't mind these pictures, we'll come back to them after the next slide. So many astronomers came to the assumption that the universe was expanding in the 1920s, but it was Edwin Hubble who provided proof of this theory through his observations of clouds of dust called nebula, which were independent galaxies, and he found out not only were these galaxies far beyond the Milky Way, but they were also moving away from us. He confirmed this recession using the spectroscopy to examine light from galaxies and found out that the light from distant galaxies shifted to the redder end of the electromagnetic spectrum, and such light has long wavelengths. So he came to the conclusion that light had to be traveling across space in order for it to be stretched to such long wavelengths. He also saw that the further away a galaxy is, the more prominent its redshift is. In other words, the more distant the most distant galaxies are moving the quickest. Now, Edwin also came up, provided a relationship that the rotation speed of a galaxy and the distance from the galaxy is from us. They obey something called Hubble's law, which states that they're directly proportional. So as if you come back to this graph, now through his various research, he plotted points on a graph and found that using the gradient you get from the graph gives you Hubble's constant, the rate at which the universe is expanding. So the further away they are, the faster they are moving. And thank you. Next, we're going to the cosmic microwave background, presented by Dylan. Thank you, Keto. So cosmic microwave background radiation. So about 13.8 billion years ago, the Big Bang occurred. And the Big Bang was a rapid expansion of the universe from an extremely hot, dense point, which we call a singularity. Now, thanks to the Big Bang, the fabric of space and time were both created. And initially, the universe's matter was in the form of a hot plasma, and light was unable to travel freely without scattering. After about 380,000 years, the universe expanded and cooled down, enough for protons, neutrons, and electrons to combine. This led to the universe becoming transparent and light being able to travel freely through space. Now, at a Bell Telephone Laboratories facility in Holmdel in 1964, two scientists, Arno Penzias and Robert Wilson, were experimenting with a highly sensitive horn antenna, which was a long antenna. It was 6 meters and it was state of the art. And it was used to detect radio waves, which bounced off of satellites called echo balloons. Now, when they were measuring these faint radio waves, they had to remove other interferences, which would cause readings and cause their data to be skewed. However, even after they removed whatever they could, the data still showed a low steady noise that remained. Now, this leftover noise, which was more intense than what they expected, came from all directions in the sky during both daytime and nighttime. And the noise had a specific wavelength of 7.35 centimeters. Now, during that same time, astrophysicists Robert Dick and Jim Peebles and David Wilkinson at Princeton University were preparing to search for microwave radiation in that region of the spectrum to find evidence for the Big Bang theory. They thought that both matter and radiation must have been scattered, and that due to a massive redshift, the radiation would be detected as microwaves. Now, Penzias was told by his friend, Bernard Burke, who was a physics professor at MIT, about a preprint paper on the possibility of finding radiation left over from an explosion that filled the universe at the beginning of its existence. He and Wilson contacted Dick as they believed this was the radiation they were looking for. Dick was invited to Bell Labs to listen to the background noise from the horn antenna, and he and his colleagues deemed this radiation as a signature of the Big Bang. Now, the next part is on supernovas, which I'll hand over to Makanakaishe.
Thank you, Dylan. So I'm going to be presenting on supernovas. Now, a supernova is the final goodbye of a dying star in the most attention-seeking way and violent way possible. Supernovas are the cause of neutron stars, pulsars, which are spinning neutron stars, black holes, and nebulas. The brightest known supernova is an SN 1006 that appeared in the Olympus constellation, and it was visible for an estimated 2 years in that time period. This is also another fun fact that shows that supernovas have been there for such a long period of time and have been helping us to discover our universe for the longest period of time. As for example, in China, it has been recorded that scholars or astronomers in China would record supernovas as guest stars. And one supernova that was recorded in 1006 AD is still pulsing today in the Crab constellation. The reason supernovas occur is due to, one, the collapse of a massive star's core due to its own gravity, which causes type 2 supernova. The core temperature of this collapsing star can reach 3 billion Kelvin. The second reason is because of the greediness of a white dwarf in a binary system. What I mean by this is that when there are two stars in a binary system, one star is going to absorb the weight of the other star, and as it absorbs the weight of the other star, it's going to grow larger. And then it's going to grow so large that it exceeds the Chandrasekhar limit, which is about 1.4 times the mass of our sun. This then causes it to violently explode and form a type Ia supernova. Now, how are supernovas used today to help us understand our universe better? They are a primary source of heavy metals in the universe, and they are what help spread heavy elements in our universe. So when a star dies, all the elements that are inside that star will be spread out across the universe during a supernova. They also control the movement of gases in galaxies and affect galaxies' evolution. This is shown in how, in our own Milky Way, when supernovas occur, they shape how our Milky Way is shaped. So if you see in other galaxies as well, those shapes or how the gases move are due to supernovas. Supernovas are also a form of rebirth as they cause the formation of nebulas to occur. They also help us better understand the universe and its evolution. Now, since I did say that supernovas are a form of rebirth, this could lead to another question, right, which is a paradoxical question. Right, so we all know black holes exist, but physicists now assume there's the complete opposite of a black hole, which is a white hole, right? So the question is, if a black hole is caused from a supernova, right, would that mean that a white hole is then caused by a nebula, since that's the birth of a star, and a black hole is caused by the death of a star, meaning they're two polar opposites? Other uses of how supernovas help us to understand is they help us calculate the astronomical distances of objects from the Earth, specifically type 1a supernovas that are used as standard candles. Discovered supernovas far from Earth are fainter than expected, and this has allowed us to be able to make the discovery of black matter, which is said to be the driving force behind the accelerating expansion of the universe. And as my colleague Keto said, that 5 billion years ago, there was the rapid expansion of the universe, and we believe that the rapid expansion is due to dark matter. I'm done with my presentation. I now leave it to Raza.
Now, at the last part of the presentation, we're going to be talking about Einstein's theory of general relativity. Eclipses have always fascinated people. Solar eclipses have been there since the birth of the Earth and the Sun and the Moon. And a solar eclipse is when the Moon blocks sun rays from reaching the Earth and causes a solar eclipse. So in 1919, there was a similar total solar eclipse, and astronomers used the opportunity to test Einstein's theory of general relativity, because during a solar eclipse, it allows them to block out the lights from the sun and only get the light from behind the sun. So in the diagram here, you can see there was a star behind the sun, and the star appeared to be in a straight line as viewed from the Earth. However, the true position of the star was actually a bit more towards the left. And this confirmed to them that gravity wasn't just a force, it was a curvature. If you can imagine rolling a ball into a blanket which has a sort of a dent in it, the ball would roll around in a circle, which is similar to what's happening here. The light from the star is being emitted towards the sun, and the sun is bending the light towards the earth. It's this sort of an angle that's being formed, which is called Einstein's angle. This one was 1.7 arc seconds. So this confirmed to them that Einstein's theory of general relativity wasn't just a theory. It is reality. It's the curving of space-time itself. So that's the presentation, and thank you for listening. One second.
Right, there we go. Thank you very much, Raza, and your team with Keto, Dylan, and Makanakaishe. It's fascinating to hear that actually your views on physics and astronomy like that, and it does us good because the ASB is trying to involve young people, and to see such a well presented and well thought out presentation like this is very good. Well done, and thank you. We do have some time left now, about 15 minutes. If anybody would like to ask a question, either of the two teachers, Mr. Setlang and Mr. Charamba, or of our four presenters, do so now. Are there any questions?
There are a few questions from Mr. Harold's presentation. There's a question about Mr. Harold's presentation.
Okay, whose?
Mr. Harold's.
Oh, yours. So, what's the question?
That should be here.
Hello, David. Can I just make a comment?
Perseus constellation contained. Right, I can answer the Messier object. Okay. First of all, I'm not familiar with Perseus's constellation and what it contains. But Messier was an astronomer who catalogued all the brightest objects in the night sky. And every one of these objects, whether it was a galaxy, a supernova, a nebula, was given a number. For instance, the Andromeda galaxy is 231. You can find lists on the internet, if you like, and in books of all the different Messier objects. I can't remember what Messier number 1 is, but I know I've got a chart at home with all of these objects listed. Yeah, sorry, and I'm sorry I can't answer anything about Perseus constellation. I'm have no knowledge about that.
Thank you, Harold.
Messier 1 is the Crab Nebula.
Messier 1?
Messier 1 is the Crab Nebula.
Thank you. Well done. True?
Give me a second.
If there are no more questions, any more questions either for Harold or for the teachers or for the four presenters, do raise your hands. Otherwise,
we'll call it a night.
I'd just like to say thank you very much to Raza and to Mano,
Yes.
who are the clever ones here. They're the ones that managed to cook everything up. Well done, and thank you very much.
Mr. Slater?
All right, I will.
Hello,
Yes.
sir.
In fact, I'd like to say, they have to attend every presentation which we hold here, because we wouldn't be able to get by without them.
Okay. That's so true, I know.
Question here to my students from the academy. They are all leaving the higher at the end of actually the whole left now, finished their studies. So they're going to university this coming year. I'm just wondering whether they left some students in the club that are going to take forward what they've done.
Students.
Thank for that.
Still there.
They will be there for the first half of the second year.
Okay.
The
Then support those who can, so that by the time you leave, the club doesn't collapse.
Yeah, because already someone.
Oh. Okay. Okay. Thank you.
What I'd like to know is, are they studying, carrying on with their astronomical studies, or are they going to physics, or what are they going to study?
Yes, they should answer.
Is that my question?
Yes.
Okay, so I left the high in 2023, and right now I study at the University of Cape Town, and I'm the chairperson of the Space Society there. And I also attended the General Assembly last year that happened in Cape Town. So I would like to think I am very involved in astronomy still, and I'd like to continue to do so. The others can answer for themselves.
Yes, I'm gonna continue with astronomy. I'm also gonna continue with astronomy. It's actually my main goal. I'm trying to get into aerospace engineering. From there, I'm gonna try and get into an institute which works with astronomy.
Which universities have you applied to?
I haven't started applying yet. I'm listing down. I'm gonna start applying by December.
Thank you, Raza.
Well, I'm doing computer, well, I plan to do computer science, right? So I'll be trying to look how the computer science can be used to further other parts of astronomy, like simulations, for example. Our computers that make calculations and stuff for us, so that otherwise we take forever to do them compared to a computer. So I'll be trying to try and get into that as well to help improve how research in astronomy is going. Yes.
Well, for me, like Raza said, I'm also venturing into aerospace engineering. So with this, I hopefully one day make a rocket so we can send it outside. Maybe even help Botswana get like a space institute like NASA, so we don't have to take our satellites to the US or to the one which is when we can reach here. Yeah.
Okay. Thank you.
So I plan to pursue aerospace engineering, and how that might relate. How that might relate to astronomy is that I want to find out why certain aircrafts or spacecraft specifically crashed or fell apart when they were entering our atmosphere. And I want to be capable of making them as they go out and come back as fast as possible. Yeah.
Okay, I think that's the end of the presentation. There's now going to be a committee meeting. So we'll switch this one off and go into the committee meeting. Thank you very much.
Thank you. Thank you, everybody. It's very good. Thanks. Bye.
Shall we go straight in the meeting?
Is it a different link?
Yeah, but right now we start immediately.
Well, I think, yeah, I'm still waiting for this call from Germany, actually. So we go